us solve the first packet of the summer assignment. Question number 1 talks about Dalton's theory. Now, Dalton has in place 4 postulates. In this case, they are expressed right here. Out of those 4 postulates, the question asks which ones out of those postulates we do not any longer consider valid. So let's analyze every single one of those. So the first postulate says each element is composed of extremely small particles called atoms. This is something we still consider true. Because, again, let's analyze the words very closely. The element is composed. So if you have the, for example, piece of aluminum, okay? So this is a sheet of aluminum made of aluminum, okay? All of those little aluminum, those are stuff called atoms. So atoms are the smallest part of the matter that still has the same properties of the element we have chosen. If we start breaking the atom, okay, aluminum, for example, like in this case, Dalton says atoms are indivisible. If we start dividing them and we have the protons, the neutrons, the electrons, then all of a sudden I find protons, I find neutrons. I do not have the aluminum atom. So the smallest part of that particular substance, okay, if we are talking about aluminum, for example, yes, the smallest part is the atom. Atoms of a given element are identical. Now, this is not true also, because if you think about the element aluminum, okay, I might have a part of matter that contains 13 protons. So to me, this is aluminum, right? Then I have another element, another chunk of matter, which still contains 13 protons. So this is still aluminum. But let's say that this matter here has a 27 AMUs, okay? And this one instead has a 26 AMUs, okay? So this is still possible, because this is telling me, okay, that I'm talking about the aluminum, which is containing 13 neutrons in this case, but 14 neutrons in this case. So this aluminum is enriched by 1 neutron. Still is a little heavier than this, but still it is aluminum because it has 13 protons, okay? So this is not true. So there are isotopes, there are stuff that belong to the same category or the same label as aluminum, for example, but they might have different number of neutrons. So they are still the same given element. There is aluminum, again, as a choice in this case, but they are not identical because the number of neutrons is different. And then the fourth postulate instead says the atoms of different elements are different and have different properties. Well, I hope so. So which ones are the two that are no longer true or considered valid? Well, the choice II and III. So this is the choice that we do not consider good. Other than that, let's go for the second question. The second question says there are so many electrons and so many protons and neutrons in the atom xenon with 54 protons. Now again, remember also how to write those values here. So he's choosing the element xenon, but because he's choosing xenon, has to be 54 protons. The xenon has to contain 54 protons. Then what is the mass? Well, we will go more in details later on during the course, but there are obviously ways of determining what is the mass of that particular xenon. because you may have a whole bucket in which you toss all the elements that we consider xenon, but then we have to identify also which of those xenon are with mass, for example, 132, which of those have a mass 133. Obviously, the more heavy they are, the more they might sink. So I'm giving you already an idea of what is going on there. But uh, again, as long as we have 54 protons, then we know we're talking about xenon. It's talking about atom, not ions. So this means that the element is neutral. So we have 54 protons, we have 54 electrons, and therefore how many neutrons we have? Well, the total mass is 132. This is the number A, the atomic mass number, and this is the number of protons and the number of neutrons. So if the protons are 54 and this is 132, then we know that the neutrons have to be 78, which is this choice right here. Okay, because we are adding those two to have a number result of 132. Now, which pair of atoms constitutes a pair of isotopes of the same element? To be the same element must have the same Z number, the same number of protons. So this is the only choice I'm seeing, okay? And which element would that be, just for the sake of it? Well, the one that has 6 protons is going to be carbon. So you have a carbon-14, another way of representing the carbon-14 is this, or you can have a carbon-12, okay? Then the element Z, why is the average mass of the isotopes not the same as adding those numbers and divided by 3? So if I was asking the average of those 3 numbers, then yes, you add them up and you divide by 3. But if I am asking the weight mass, then I will not just add and divide by 3. Now the reason is the following. Let's say that I have a box, okay? And in this box, I have 3 categories of stuff, okay? So for example, I have trains, I have dolls, and I have cars, okay? Now, I have train-wise, for example, I have 2 of those, okay? Dolls, I have, for example, 15, okay? And in cars, I have, let's say 3, okay? So, if each train, okay, has a weight of, let's say 100 grams, okay? Each doll has a weight of 0.5 grams, and each car has a weight of 1 gram, okay? I want to know the average mass of this type of things, okay? So how would I do it? Okay, I cannot just take 100 and 0.5 and 1 and add them up. If I would do that, if I would not know any better, I would take 100, I will take 0.5, and I will take 1. Okay? So this means that I have a 101.5 grams. Okay? Then I divide by 3, because it's 3 categories. Okay? And I have 33.8. Okay? So this is the average mass according to what we usually do in some circumstances. Now, in this case, instead, what happens? I have 2 trains, so I have a 200 grams of a train. I also have 15 of those 0.5 grams. I have a 7.5 grams coming from here. And I also have a 3 grams coming from here. Okay, so this gives me 200 plus 10.5, so 210.5 grams. This is if I add everything. Then, if I divide everything by the total number of stuff, this is divided by 20. So if I divide this one by 20, I have 10.5, okay, grams, which is different from this number. Also, what happens instead if I consider the abundances, okay, of every single one of those things? So I have 100 grams, but 100 grams is present for 2 times over 20, okay? And then I have the 0.5, okay, which is present for 15 times out of 20. And then I have the 1 gram, which is present for 3 times out of 20. Okay, so this means I did a 200 plus this multiplication here, which is the 7.5, plus the 3 times 1 divided by 20. Okay, which is exactly what we have here, which is the 10.5 grams. Okay, so those two methods are exactly analogous, as you can see, but this method is really, really wrong because it's not considering, okay, that this is the representative weight of the isotope cars. This is the representative weight of the isotope dolls. This is the representative weight of the isotope train. All of those isotopes belong in the category toys. Okay, so we cannot just add and divide by the number of different toys, but we got to consider the total weight of the particular category of the toys. Okay, and divide by the total amount of toys that we have, not the categories. Okay, so here we are just adding representative weights and we are dividing by the categories. We can't do that. Okay, we have to divide by the number of toys. So I hope this makes sense so that we can move to can now work with those categories instead. So we have those masses. Those are the representative masses in the category for the isotope 221. So this means I have a 220.9 AMUs, okay? But this is present 74.22. So I have 74.22 of those 220 stuff. Okay, so I have 74.22 of those. Okay, then I have the 220, but those I have 12.78 of those because this is the abundance of this particular category. Okay, and then I have 218.1 times 13, which is the new also amount, okay, of this mass, okay, out of the total thing. Now, what is the total thing? Well, the total thing is 100 if I add them up, okay? That's why this one I can say, so if I really wanted to go more in detail for this, I can say 229.9, 74.22%. It's still the same thing, right? So I'm considering the percentage of this, and 220 times the abundance, which is 12.78%. And I also have 218.1 times 13%. Okay, so I can write it this way, or I can write also, instead of writing this, I can write 74.22%, it's still the same thing, right? Or 12.78%. and this 13%, I can do that. Or I can write point, 7422 or point 1278 or 0.13, right? All of those are exactly the same things, so I have to multiply by one of those, whichever you like. Still, it means exactly the same thing. So this is going to be the average that we are looking for, okay? So also one more thing to keep into consideration is the significant figures. So this is 4 digits, 4 digits, 4 digits. I must have 4 digits. So this one is going to be your choice, not this. Okay. Now the reason is because you do not have any guessing on this number after the decimal. For the centesimal part of your number, you do not have any cents. Okay, so it's not worth it, okay, for you to say N42. So basically what this means is, let's talk about money instead, okay? You have $220 and 10 and 10 and 9, I want to say 9 tenths, okay? So 9 dimes. So then you have $220, okay? And this one instead you have $218 and 1 dime. So I can write this $20 and 9 dimes. Okay, $220 and 0 dimes. Okay, and here I have 1 dime. Okay, so you do your average and you find 220 and 4 dimes. But for this one, to say that you have $220, 4 dimes, and 2 cents, who has ever talked about cents here? So nobody's telling you that you actually can consider this 2 cents. Nobody was using this currency. Nobody talked about cents. So you have no right to call somebody and say, wait, I owe you 2 cents. Where are those 2 cents coming from? Okay, especially because the cents you don't know. Okay, so this one could be and 7 cents, this one could be a 9 cents, this one could be 1 cent. If you add also those, chances are you're not going to have a 42. So if you're not considering cents, therefore you cannot give a cents as a remainder, okay? Or add them up and say, well, you owe me 2 cents also. There's no cents involved, okay? So other than that, the other problem is silver has 2 naturally occurring isotopes with the following isotopic masses. So again, what this means is that you're talking about argon, okay? So if we are talking about argon, we are definitely talking about 47 as a Z number of protons, right? Now what they are doing is they are considering 107 as general mass, but in reality you have 2 isotopes, okay? So this is already the average, but they are making specific that you have 2 isotopes. One that has a 106.9 and the other one that is 108.9. Okay, so so how much of this do I have, and how much of this other argon atom instead do I have? So I know that I have those 2 masses. Okay, let's just write 0.9 because it's not important right now. Okay, so 106.9. But you don't know how many of those you have, okay? And then you also have the other mass, okay? And also for this one, you do not know how much you got, okay? But you know that the total average, okay, is going to be 107 point, let's say 9 again, okay? AMUs. So how much of this and how much of that do I have? Okay, so in this case, what you do, okay, is instead of just guessing, so we want to know what is the percentage basically, okay? Because I don't know how many are in total. So basically, if I consider a average of 100, okay, as an average number, I have X out of 100 is going to be present with this mass, And for the y, instead of writing y, okay, I know that if this is 5, this one has to be 95 because the sum of those has to be 100. So if this is x, this one is going to be 100 minus x over 100. Okay, at this point I will just solve. Okay, how are you going to solve? Well, you just solve, right? So you have 106.9 x and 108.9 times 100, if you can write it like that, minus 108.9 x equal to this one times 100 instead, so 107.90, right? And then you just put the stuff together. So 106.9 minus 108.9, those are the x's, and this is equal to 107.90 minus 10890, right? Because you're multiplying this one by 100 as well. At this point, your x is going to be equal to this C. Okay, if you solve. Now, this number 6 instead, which of the following conclusions can be drawn by J.J. Thomson plus plum pudding? Well, atoms contain electrons. Yes, that's a good choice. Practically, all the mass is contained in the nucleus. No, he does not know that. Atoms contain protons, neutrons, and electrons. He has no idea that there are neutrons still until 1931, I think. Atoms have a positively charged nucleus. Again, no, he does not know. And no two electrons can be the good. He doesn't even know what quantum numbers are. Okay, so this is the only choice that we have. Then, next questions from 7 to 9. So we have those choices only for answering those questions. So either the wave nature of matter, why matter is made of waves. Well, orbitals are waves, let's put it that way. Okay, orbitals are waves. Okay, spectral lines, well, we know what spectral lines are, I hope. Quantum number, we know those. So the spectral line, okay, let's just, spectral lines are the absorption, for example, lines of the atom. And then quantum numbers, well, you can have the quantum number n for the level of energy, you can have the orbital shape, you can have the ML that tells you which of those shells you're talking about, and then the spin. And then we have Bohr model that has the ugly atomic model, okay, with those rings. So according to the meaning of this, what can we answer for question number 7? Explain the spectral lines by postulating that electrons were only able to exist in discrete orbit of different energies around the atom. Well, it looks like this is the atom that they are talking about. The spectral lines, those are connected, right? But those spectral lines identify only electrons in very specific levels of energy. So this is the Bohr model. Then describes location of electrons series of possible quantum states. Well, this one seems like it's the quantum numbers. And then caused by electron emitting energy as they transition. So this one has to be the spectral lines. Okay, and then 10, which of the following is a correct interpretation of the results of Rutherford experiment? Well, he discovered actually the nucleus, so the same number of no. The electron atoms are arranged in shell, no. Neutrons, he doesn't even know what neutrons are. Positive charges are concentrated in a small region called the nucleus. So that's a yes. So this is your answer. Then energy of a photon of light is proportional to frequency and what proportional to the wavelength. So first of all, the energy of a photon is given by h nu. Nu is your frequency, lambda is your wavelength. So if this is the frequency and it's not a v, okay, it's a nu. So h is your Planck's number. So h means 6.626 times 10 to the negative 34. The units, we will see those later, but those are joules per second. Here, joules seconds, let's just put it there. And then also, we know that the frequency is equal to c over lambda, where c is the speed of light, right? 3.00. I need the 00 because otherwise we only have one suffix, and instead 3 are a little better, divided by the wavelength. Okay, so if this is true, okay, and it is obviously, then we have basically, we can write those things. We can say that E times nu is equal to H, okay? And also, so let's start with this one. So how are, E divided by nu? So E, from here, we can say that E divided by nu is equal to H. So if this is a constant, and I make this one twice as big, okay, to keep the H equal H and not twice H, I got to also multiply by 2 the frequency in such a way that they simplify, okay, they cancel out, and I still have the number. So it looks like whatever I'm doing to E, I gotta do it to the frequency as well. So those are directly proportional. Now instead, what happens to the wavelength? Well, E can also be expressed as H and then C over lambda, which means that E times lambda is going to be equal to HC. This is also a constant. So if I multiply by 2 the E, for example, okay, I got to divide the lambda by 2 in such a way that they cancel out. So this one is going to be indirect instead. Okay, so directly and indirectly, inversely, whatever, this is the D. What is the wavelength of a light of this many nanometers? No, he wants it in nanometers. That has a frequency of. So this is the nu. I want the wavelength. So C divided by the frequency is going to be the wavelength. So I have a 3 times 10 to the 8th 0.00. Okay. So 3.00 times 10 to the 8th divided by the frequency, which is 3.22 times 10 to the 14th. Okay, this is meters. So let's try to not forget, okay, the units of those. So this is the speed of light, which is meters per second. This is 1 over second because it's your hertz, is the frequency, right? So meters per second divided by 1 over second means meters, okay? So this is going to be, for example, 3 divided by 3.22 times 10 to the negative 6. Okay, so this means that if this 3.22 were a 3, then this one would have been 1 times 10 to the negative 6. So it could have been something like that, right? But this is positive. Also, what I notice is that, so I have something close, which is this number here, okay? So when I do the things here, the division, I have actually this number right here. But this is not the answer because, so first of all, why is this the same as that? Well, this is 3 divided by a number bigger, so this one has to be smaller, right, than 1. So 0.9, for example, times 10 to the negative 6, which I can write as a 9 times 10 to the negative 7. So here, without doing calculations, we see that we are in this range here. Now, why would this one be wrong? Well, because those are meters, right? The problem is asking specifically nanometers, okay? Nanometers is 10 to the negative 9, okay? So how do I make this one a 10 to the negative 9? This is smaller, right? So I got to make this one bigger. So 900 10 to the negative 9 means 900 nanometers, okay? So if now we do, there's no reason because this is the only 900 number, okay? So this one has to be your choice. Otherwise, you just do the multiplication and you see it. And then the energy of a photon that has a wavelength of 9 is the energy, okay, is h times the nu, okay? But I have the wavelength, so I got to do the hc divided by the wavelength, okay? So this is going to be your 6.626 times 10 to the negative 34 times the 3.00 times 10 to the 8 divided by the lambda, which is 9. Okay, so this one again, I believe, to be honest, that they said at the beginning to not use the calculator. Let's see, because I do not remember. No calculator permitted, right? So okay, so let's see what happens. Okay, so without calculator, what can we say? Well, we have a 6.6, we have a 3 and a 9. So first of all, we can simplify the 3 and the 9, so we can have a 3 here. Okay, then we have a some kind of 6 divided by 3, so this one can be about a 2.3, right? Because we have this one. So 2.2, right? Let's remove the 2.6. Okay, so this is somewhat 2.2, and then we have times 10 to the, we have a 34, negative 34 plus 8. This is a negative 26. Okay, do we have anything like that? Well, yes, right here. Okay. And I'll stop this video here so that we can do the periodic table in a different video, okay?